everyone. In today's lecture, we're going to cover some more properties of the determinant of some matrix with entries in some commutative ring R. So last time, we took some matrix A with entries Aij in some ring R, where R is a commutative ring. And then we defined the determinant of A by some formula which is given by some sum over the set of all permutations of 1 to n. So the determinant was defined by the formula that A is defined to be the sum over all permutations of the sign of the permutation times A1 sigma 1, A2 sigma 2 up to AN sigma n. And we proved last time that the determinant of a matrix equals the determinant of its transpose. And as a consequence, we could also write the determinant by a slightly different formula, having instead the permutations act on the first subscript. So we also have the formula that A equals the sum over all permutations of the sign of the permutation times A sigma 1, 1 up to A sigma n, n. And sometimes one version of the formula is more useful than the other version. Okay, so the last thing we saw in the lecture from Wednesday was that we could view the determinant as a multilinear alternating function acting on the space of column vectors. So we also saw that we could view determinant as a multilinear alternating function. So to do this, we should define a space of columns. So set E to be the module R to the n, where we represent elements in R to the n by column vectors. So take some elements, C, given by some column vector, say with entries C1 up to Cn in R to the n. Then we're going to define a map which should be some n multilinear map. So it takes as input n different column vectors and gives as output some entry in R, so some scalar. So we define a mapping det from E to the n, so the set of n different column vectors with target R, and it's defined as det of n columns, let's say C1 up to Cn, where these are all column vectors, is the determinant of the n by n matrix that you get with C1 up to Cn being the column vectors. Okay, so we're viewing these. So these are column vectors. And then determinant takes as input n column vectors and gives out some scalar that you get by taking the determinant of the n by n matrix with columns given by the input column vectors. Okay. All right, so let's prove that this function actually gives you a multilinear alternating map. So proposition, the mapping det from e to the n to r is itself multilinear and alternating. Okay, proof. So let's first prove the multilinearity part of the proposition. So to do this, write each column vector as, so let's give it entries C1I up to little c and I. And we do this for each of the n columns. Now let lambda be some scalar in R, and let dj be some additional column vector. Okay. So what we have to do is we have to evaluate the determinant in the jth entry. We have to see what happens if we take a linear combination of the jth column vector of the matrix C together with the column vector dj. So we have to evaluate det C1, cj minus 1, and then in the jth entry we want to put cj plus lambda dj. Then I'm going to have the rest of the column vectors of the matrix C. Okay, so this is the jth entry. All right, so now we just use the formula. So this is, so we now have that this, just plugging in the definition for the determinant of the n by n matrix with these columns. This is the sum over the sign of the permutation times the entries C1, sigma 1, up to C, and then the jth entry will be Cj, sigma j, plus lambda dj, sigma j, times the entry Cj plus 1, sigma j plus 1, C n, sigma n. Okay, but this sum can be rewritten as the sum of the sign. So we're just going to factor this out, this term here. So this now becomes the sum of the permutations sine of sigma C1 sigma 1 Cj sigma j up to Cn sigma n plus lambda times the sine of C1 sigma 1 up to d j sigma j. And now this is the jth entry. All other entries are unchanged from the determinant of the matrix C. Okay, so the first term is the determinant of C1 up to Cn, whereas the second term is lambda times the determinant C1, then with jth entry, dj Cn. So this equals determinant C1 Cn plus lambda times the determinant C1 dj Cn. And this is what we needed to prove for multilinearity. Okay, so multilinearity is now established. Okay, so let's check that determinant is alternating. So the determinant, so what we have to do is we have to swap two columns. So the determinant of C1, Ci plus 1, Cn, we have to compare this to the determinant that we would get if we were to swap these two columns. Okay, so let's just start by expanding out the definition of the determinant. So it's given as the sine. So let's use the transpose definition. So it's a sine of sigma C, and we can write here sigma 1 1 using the comment I made at the start of the lecture that since the determinant of a matrix is a determinant of the transpose, we can have sigma act in the first of the lower subscripts. Okay, then this will be sigma I C sigma n. All right. So now we want to see what happens if we swap two columns. So let's introduce the permutation that swaps I and I plus 1. So let tau equal I plus 1. This is the transposition which swaps I and I plus 1. So the transposition, if you multiply by the transposition, you get a bijection from Sn to Sn. So multiplying or having a transposition act gives you a bijection. Let's have it act in, let's pre-multiply by the transposition. Then we would get a bijection. So as a consequence, this sum is the same sum as, well, it would be the same as if I would take one of these terms for each of the permutations pre-multiplied by tau, since it gives you a bijection. So it's the same. This sum here up above, this sum here, is the same as the sum sine sigma tau C one up to C sigma tau I C sigma tau I plus 1 up to C sigma tau n, because as sigma runs over all Sn, then each term from the previous sum here appears precisely once here, since pre-multiplication by tau gives you a bijection. So the previous sum is the same as this sum. Okay, and now we can rewrite this. So tau fixes all elements other than 1 or I plus 1. Right, tau x equals x unless x is I or I plus 1. So this is the same as the sum let's just leave this here for now. So it's the sum over the sine of sigma times tau of, so this first term here will be unaffected by tau, since tau fixes 1. So it fixes all terms other than I or I plus 1. So it's going to be, the first term will be sigma 1. And then the first term it changes will be I, becomes sigma I plus 1 I. Then we have sigma I plus 1. And all other terms are unchanged. Okay, but we already saw that if you multiply a permutation by a transposition, the sign changes by 1. So the sign changes by -1 rather. So this becomes negative sine sigma times the previous expression. So let's rearrange this slightly. This is negative. So let's just rearrange this by replacing the I plus 1 and ith entry in this. So let's write this as sine sigma, C sigma 1. Then let's just swap these two entries. So since it's a commutative ring, I can swap my entries around. Okay, and now this term is precisely the negative of the determinant of C1 up to, so you see that it's the same as the determinant of this with the ith entry now Ci plus 1, and the I plus 1th entry Ci. So we've swapped these two columns at the expense of this negative sign. And that's what we needed for alternation. Okay, so that's now proven, and as a consequence, the theorem is now proven. Okay, so we've shown that determinant defines an alternating multilinear map. Okay, so we get a lot of nice consequences as a result. So one consequence that we have is Kramer's rule. which tells you the following. So let A1 up to AN be column vectors of some matrix A, and let B be some linear combination of the column vectors. So we have some matrix, and then we take some linear combination of the column vectors. Then Kramer's rule will tell you what happens if you replace the ith column with this linear combination. So Kramer's rule tells you that the determinant of the matrix obtained by replacing the ith column by some linear combination, so the determinant of this thing, and it tells you that this is just lambda I times the determinant of the matrix A. Okay. So this is a direct consequence of the fact that determinant provides a multilinear alternating mapping on the columns of a matrix. Okay, so the determinant, so let's start with this entry. So this thing, this is the determinant of A1, AI minus 1. Now let's sub in the formula for B. So using the multilinearity, this is a sum sorry for the noise. Like this. So that's just using the multilinearity. So we can pull out also the scalars lambda j. So as soon as a column repeats itself, then we know that the determinant is 0 since it's alternating. So this term here is 0 as soon as the column AJ is in the set of the other columns, which is the same as saying that J is not equal to I. Okay, so this expression here is simply equal to so this is 0 unless I equals j, so we have lambda I det a1 ai minus 1 ai plus 1 an, which is lambda I times the determinant of a. Okay, so we've proven Kramer's rule. So just notice here that the only coefficient, so it tells you about the determinant of a matrix where you take a linear combination, where you replace one column with a linear combination, is just given by picking out the coefficient in front of the entry for the corresponding column. So if I replace the ith column by some linear combination, then it's just the determinant of the original matrix times the coefficient, lambda I, in front of the corresponding column. Okay? So we have some immediate consequences of Kramer's rule. It's a very useful rule. So I'm going to write M, N, and R for the set of all n by n matrices. Then let's just give one consequence of Kramer's rule. It tells you that that if I take two matrices, then the determinant of the product is a product of the determinants. Okay, so to prove this, let me write my matrix A out in terms of the columns. And let me just write B out in terms of all the entries. All right, so we should remind ourselves how to take a product of two matrices. So let's just refresh our memory by multiplying two matrices. Let's say 1, 2, 3, 4, 5, 6, maybe 7, 8, 9. Okay, so to multiply this 2 by 3 matrix with this column vector 4, 5, 6, we would do 1 times 4, 2 times 5, 3 times 6. So 1 times 4 plus 2 times 5 plus 3 times 6. And then the second entry would be performed in the same way using the second row. Seven times 4 plus 8 times 5 plus 9 by 6. And we could write this as, if we wanted, 4 times 1, 7. So that would be this term here. So let's group these into 3 terms. So we could write the product of these two matrices as 4 times the column vector 1, 7 plus 5 times the column vector 2, 8 plus 6 times the column vector 3, 9. So what we've done is, if you go back and look at the original matrix, it's telling you that the columns of the product are given by linear combinations of the columns of the first matrix, so linear combinations of these columns, with the coefficients coming from the second matrix. So these coefficients, 4, 5, and 6, are the entries of the second matrix that we're multiplying by. Okay, so this works in general. And what we have is that the ith column of AB is a linear combination of the columns A1 up to AN with entries coming from the ith column of B. Okay, so the determinant of AB, well, to know the determinant, we just need to know the columns of the matrix, and we know these. These columns are given by the linear combinations of the columns of A with entries coming from the corresponding columns of B. So this is the determinant of B11. So the first thing we need to do is go down the first column of B and write the corresponding linear combination of the columns of A. So setting I here equal to 1, and then taking the linear combination of the columns gives us that the first entry in the product is this. And then we have that the second column of the product is given by taking the entries B1 to A1 up to BN2 and so on until B. The last column is B1N A1 up to BN AN. Okay, so now we've got something like this, but what is very helpful is to recall that determinant is a multilinear alternating function. And we've already worked out how the value of a multilinear alternating function changes when you take linear combinations of the entries. So since determinant is multilinear and alternating, and now we've taken entries, which are some linear combinations of entries A1 up to AN, we can write this in terms of determinant of A1 up to AN, to determinant of A. So we can write this, since determinant is multilinear and alternating, as the sum over all permutations of the coefficients permuted, so B sigma 1, 1, B sigma n times the determinant of A1 up to AN. So I've just used here the formula for some multilinear alternating function where we replace the, where we're looking at the value on some linear combination of entries. So I replace, instead of looking at the determinant of a1 up to an, if I take a linear combination of the a1 up to an as above, then the determinant, then for any multilinear alternating function, it's just given as a summation like the one above. Okay, so this is now, well, this thing here, this term here does not depend upon sigma, so we can pull it out. So this is the sum like this. And then this first term is the determinant of B. So that gives you the famous property of a determinant, that the determinant of a product is a product of determinants. And this is probably the most important property of a determinant, the thing which makes it so useful. So let's end today's lecture.